Okay, in this problem, we have a ball bearing that's placed on a spring and it's compressed. And then we let the spring go and the ball flies up. And we want to be able to calculate the spring constant given the mass of the ball bearing, the distance that the spring is compressed, and the height that the ball travels. So right away I can tell this is going to be a conservation of energy problem because we're given a spring that's compressed and a height that the ball goes. So we can take a look at this and we can define our initial and final positions. Our positive up direction. Our initial position 0 is going to be right here where the spring is compressed. So that's our height of 0. And initially the velocity is also 0. And up at the top is our total height that the ball bearing reaches, and our final velocity up there is 0. So those are our initial and final positions. And to start off, I'll just make the equation for conservation of energy. So we have kinetic energy, initial, plus potential energy from gravity, initial, that's your height of the ball bearing, so your gravitational potential energy, plus our potential energy of the spring, our elastic potential energy. That's going to equal the final of all these, our kinetic energy final, plus our gravitational potential energy final, plus our spring potential energy final. So now I want to take a look at these and figure out which are 0. Which of these are 0? Kinetic energy initial is going to be 0 because there's no velocity at start. So 1/2 mv squared, this is 0. 0. Gravitational potential energy initially is also 0 because our height is 0. mgh is 0. Spring potential energy, we have potential energy from the spring because the spring is compressed. Final kinetic energy of the ball is also 0 because up at the top of this, the ball is not moving. Final kinetic energy is 0. Gravitational potential energy final, we do have potential energy final because we have a certain height to that ball bearing. Spring potential energy final is nothing because initially the spring is compressed and after it shoots the ball off, it's not going to be compressed anymore. It's going to be at its unstrained length. So potential energy of the spring is 0. So basically all we have is the spring potential energy initial is equal to the potential energy of the gravitational of the ball bearing final. So let's write this down. Potential energy of a spring is 1/2 kx squared, where k is our spring constant and x is the compression of the spring, the distance away from unstrained or unstretched length. Potential energy gravitational final is mgh. Okay, so what we want to do is solve for k here. So I'm going to multiply 2 over to this side and divide by x squared. So now if all I got to do is plug all my numbers in here and we'll get our final answer. So I'll write this up here. We have k equals, so 2 times mass of 1.6 times 10 to the minus 2, 1.6 times 10 minus 2 kilograms times our gravitational constant of 9.8 meters per second squared times by our height of 5.8 meters. Now this is all divided by x squared. X is 6.7 times 10 to the minus 2 meters. 6.7 times 10 minus 2 meters all squared. Okay, so if we plug this into our calculator, we get k equals 405.186. Now let's check the units. Okay, we have m times g, kilogram meters per second squared, is newtons. And we're going to have meters squared and meters up top, so we're left with a meter on the bottom. Newtons per meter, and that's what the spring constant is in, newtons per meter. Now, we know we have two significant digits in all of our givens, so we can say K equals 4.1, rounding to two significant digits, times 10 to the 2, and 2 newtons per meter. And that is our final answer.